Exercise 10 is a question about fair selection process when it comes to race. So we have a county in Missouri. We know the racial distribution in that county, and we've got a sample of 275 potential jurors identified by their race. And we just want to make sure that this sample of jurors is truly random and that there's not some sort of racial bias happening in who serves on the jury. And so this is a chi-squared goodness of fit problem. And so to begin, we'll state the null hypothesis. The null hypothesis here is in terms of the probabilities. It's saying, what's the probability that a white person is chosen on this jury? And if everything is fair and nothing is going on, then the probability should match the actual proportions that we already know. So the first probability for the first category should be 0.72. The second probability for the second category should be 0.07. The third probability for the third category should be 0.12. And the fourth probability for the fourth category should be 0.09. So that's how it works. And of course, the categories here correspond to each of the rate. Oops, I got that wrong. This one goes there, there we go, there, and there. Okay, so that's the null hypothesis. Nothing is happening. The probabilities for each person, for each category, actually match the probabilities that we know the population follows. The alternative hypothesis just says, hey, at least one of these is different. At least one of these four probabilities is actually different. It doesn't specify which one is different, but something isn't fair. That's the alternative hypothesis. Okay, so to compute the expected count for each cell, all you're doing is you're taking these probabilities, which are these, and you're multiplying by the total number. And so you can do that yourself. 0.72 times 275, you get 198, 19.25, 33, and 24.75. That's what we would expect if everything was exactly fair. And then you know chi-squared, how to do that. It's the same formula. You're taking your observed count, 205, minus your expected count, square the difference, divide by the expected count, go to the next one, add it up. And of course, we don't expect this to line up perfectly. We expect our observations not to be exactly the expected count, but we want it to be somewhat close. And so this is the chi-squared allows you to measure if how close is just close enough and the change is due to sampling, or is too far away and something's actually going on. So that's sort of the end goal of this test here. Let's just compute chi-squared. So we get 26 minus 19.25 squared over 19.25. We get 25 minus 33 over 33. I got to square the top, almost forgot that. Then I want to say 19 minus 24.75 squared over 24.75. Let me just show you on the last one again where everything's coming from. It's just your observed count minus your expected count. Square the difference, divide by the expected count. And so when you add all of these together, you should get 5.89. And then we're asked, of course, what degree of freedom should you use? So in this case, the degree of freedom is just your number of categories, subtract 1, so the degree of freedom is just 3.